Is Andrew Turner, and he's going to talk a bit more about some of the grain size controls on rheology.
Thanks. Okay, so I'm a postdoc with Rich, and I've been working on this with Rich and Mark, and it's a talk about the grain size and rheology as controls for mid-ocean ridges. A lot of, well, the last talk gave a great introduction for me, so I'll try and skip over this relatively quickly. But I mean, the setting is mid-ocean ridge, so we've got upwelling mantle. And the upwelling region is fairly wide. And so the question becomes, how is melt focused towards, let's say, a relatively narrow region right here? So Sparks and Parmentier put a model forward in 1991, where melt rises vertically under buoyancy and then comes into contact with this crystallization, this freezing zone at the base of the lithosphere, which makes the mantle change from permeable to impermeable. And then along this boundary, melt collects and is transported efficiently along towards the ridge axis. So a schematic of what's going on is down here. So we have upwelling, melt which is traveling vertically under buoyancy, and then the interaction with this freezing front means there's a reaction force of the compaction pressure, which has a component that acts towards the ridge axis, and so drives melt towards the ridge axis from a purely buoyancy force. So Spiegelman pointed out in '93 that with a freezing front, there's two possibilities. There's the possibility that the freezing causes an impermeable boundary, like described beforehand, when melt is directed up towards the ridge axis. And the other possibility is that the freezing is not as efficient at pulling melt down here in the decompaction channel, and so just serves to freeze into the lithosphere and causes an enrichment. So these are the two options that arise from the idea of a freezing front that can transport melt towards the ridge axis. And so in this paper, he constructed a model where there's a freezing zone with a slope boundary, and if the freezing rate was fast, just as expected, I suppose, this high melt fraction channel appears, and then you've got compaction waves that propagate away from this disturbance. But effectively, the mantle is becoming going from permeable to impermeable on a very short time scale compared to the compaction length. And so there is a high melt fraction channel that develops here and can transport melt. If the freezing rate was slow, so that the mantle changed from permeable to impermeable on a length scale that was relatively long compared to the compaction length, then what was noticed was that there isn't a high melt fraction channel, and enrichment results, which is shows us the two end member states of this. And then if we look at output from Rich's 2010 paper, we can see that what we have is a high melt fraction channel along the top, a relatively uniform melt fraction in this region where it's rising under buoyancy, and the melt is extracted along here. Yeah, I think that's what I really should say about that one. So then we move on to the recent magnetotelluric observations, which I guess is the third time we've seen those this morning. And as said in our the past presentation, one of the key things to note here is that this is where you'd expect the base of the lithosphere through thermodynamic reasons, just half-space cooling. And what you have is a relatively sharp, say 45-degree boundary to where the conductivity changes from relatively conductive to not very conductive, which implies that there's a large degree of melt here, and then for some reason there may not be melt across this boundary. More importantly, though, I suppose what you can say is there is no sign of a high melt fraction channel along this base with a relatively uniform melt fraction going to depth. So this is an interesting question or raises an interesting question as to why we should see such a picture like this when what we would have expected to see was such a strong signal along here and relatively uniform down here. So one of the things I'll be focusing on for this talk is grain size and its effect through permeability and through rheology, and how that affects the melt transport as a result. So what I have here is just a diagram from Hansen 2011, which shows how complicated the rheology can be, from a diffusion to a grain boundary sliding to a dislocation creep mechanism, where they're all sensitive to the differential stress or the grain size to a varying degree. So what we see here is grain size along the x-axis, along the bottom, stress, differential stress along the y, and then we have contours of strain rate. And then on the other side, again, another picture we've seen a fair amount of, just to highlight the importance of grain size when it comes to permeability, as the melt collects at the boundaries between grains, so the grain boundaries coats them and forms some form of a permeable network in which the melt will flow. So I'll begin by presenting you with a single phase model. So I'll only be using Stokes flow with no melt to show you the distribution of grain size that we would expect. And then I'll build on that with introducing it to a two-phase code and see how the predictions made from the single phase transfer to the two-phase. But in order to do that, first I'll need to introduce you to the grain size evolution equation as we'll be using. So we'll be using a continuum grain size evolution model, and it will just be a superposition of a growth rate and a reduction rate. So I'll first step you through the reduction rate. So grain size reduction happens because there's an input of energy, mechanical work into the system. And this mechanical work then corresponds to an input rate by just taking the time differential. It's then assumed that some fraction of this work is dissipated as heat, and some of it is used as work for changing the grain size. And the fraction that's dissipated as heat is 1 minus lambda. Additionally, it's assumed that there's only the fraction of work done through dislocation-related processes. So the rheology is a composite of dislocation creep and diffusion creep. And so it's only the dislocation-related work that goes into reducing grain size. And that's captured here in the beta, which is described here, sorry. So it's the work done by dislocation creep over the total amount of work. So that tells us the amount of energy we have to play with. And then we can work out what the energetic cost for a change in grain size is. It comes out as a grain size squared relation for the amount of energy that's required to change the grain size. Right, so what we have is so putting those parts together, we have a change in grain size is equal to the work that we've put in and the energetic cost is to produce extra grain boundaries within the representative volume. Grain growth follows the classic Arrhenius relationship, such that there's a temperature-dependent part with a prefactor, which is the mobility of grain boundaries. And then this part here is related to the grain curvature. So grains with a the rate of grain growth is proportional to the curvature of the grains. And then putting it all together into a steady state evolution equation, we have an advection term, a reduction term, and a growth term. And this is just the paleowatt meter of Austin and Evans 2007. Mark used this in a paper in 2009, compared two different paleowatt style ways of getting at the grain size, and compared them against two experiments. So one was done as a wet experiment, one was a wet experiment, and the other one was a dry experiment. And you can see that the data can be fit with this model using the various grain growth exponents here. So exponent of 2, sorry. This here is the grain growth exponent. It determines how the curvature is related to the rate of grain growth. And then also there's the Arrhenius part here. So this is the activation energy. And so this has been calibrated to these experiments, and we use the data, the values that he quoted. Observational constraints on grain size. This is a xenolith, an example of xenoliths. And the grain size that we're typically expecting is 0.1 millimeter to about a centimeter. So this is an example of the output for a single phase grain size evolution model using Stokes flow. What we have is three, sorry, let me talk you through the panels. So we have a distance from the ridge axis along the bottom and a depth along the y-axis. We have grain size, the dislocation work, the strain rate, and the viscosity. What you can see is that the dislocation work rate, the viscosity, and the strain rate are all highly correlated, and that's because this region is dominated by dislocation creep. We then have three distinct regions in our model, which have been indicated by these solid black lines, region 1, 2, and 3. Region 3 is a relatively stagnant region and very warm. And so the grain size in this region is the largest in the model. And we get the grain sizes up to about 3 centimeters. Region 2 here coincides with the region in which most of the work is mechanical work is being dissipated into reducing grain size. And so we have a reduction in grain size in this region. Region 1 is then the coolest region of the model. And we can see that this is the 1200 and this is the 600 degree isotherm. So what we have here is effectively very little growth from any material which is advected across over here. And this small grain size lid is solely the result of grains that have been reduced very heavily here and advected across. So this was for a spreading rate of 4 centimeters a year. And we look at the sensitivity of how this sort of structure changes with change in potential temperature, grain growth exponent, and spreading rate. And what you can see is that although the actual magnitudes, so the colours become more blue and yellow, or more yellow and red here, it's shown more clearly, I suppose, in the probability distributions across the bottom. So we have a log 10 grain size, so 1 millimeter, centimeter, 10 centimeters in probability density. And so this blue one corresponds to the distribution for cold and red for hot. And what you can see is that it's just been translated over to a larger grain size. So in fact we know that the distribution has remained the same as a function of space. It's just become larger grains by increasing the temperature, which I suppose is something you'd expect. The sensitivity to the growth exponent contracts the distribution width. So with an exponent of 2 where our grains grow more rapidly, we have a most extended distribution coming out to here. Whereas with a P of 4, grain growth exponent of 4, we have the most contracted one, and so our largest grain size is about 3 centimeters. However, I would say that, again, the spatial distribution is relatively similar. It's just there will be stronger gradients in the P equals 4 than the P equals 2 case. And in the spreading rate case, the sensitivity to spreading rate is slightly different. So this is a very slow spreading rate of ½ centimeter a year, and this is a spreading rate of 7 centimeters a year, so quite a fast one. And what we see is that the region of large grain size is contracted against the ridge axis, forms a nice triangular region here, and we're reducing grain size quite systematically as we go up. Again, this is the region of most mechanical work, and this is a region where it's dominated by being cooler. In this case, we have a reduction here in grain size because there's a stronger sense of shear in this direction, where the beneath the ridge axis is going faster than here, and it's reducing the grain size in this region, as well as the reduction that was seen here. So with these grain size field structures, we can estimate a background permeability, estimate a permeability. And so we take a reference value of 1% melt and look at what it would do to the permeability beneath a mid-ocean ridge. And what we see is that we have, for the slow case, is a bit of a bit different because it's so slow. So I'll probably just talk about these two actually. What we see is that, well, in all cases, region 1 is a region of reduced grain size and so reduced permeability. And it's always on top of a region of the greatest grain size in our domain, which means increased permeability. And so what we have as we go up vertically is a reduction in permeability. We therefore propose that this could act as some form of soft grain size permeability barrier, as we're having a reduction in permeability, which is again inclined, like the first cases I showed you, like the Sparks and Parmentier permeability barrier. This is a very soft version of the same thing. So we have a reduction in permeability in the buoyancy direction, which could produce a back pressure from compaction back pressure, which curves the flow around. So we then test this idea with a two-phase model. So these are the equations of the two-phase model. I suppose what I want to focus on is we've introduced a temporal element to our grain size model. The permeability is grain size squared and melt fraction to some value, and we have the ability to use a grain size sensitive and strain rate sensitive rheology. So the m would be a grain size exponent for the rheology, and the n would be a strain rate exponent, such that if m was 3 and n was 1, we'd have diffusion creep. And if n was, say, 3.5 and m was 0, we'd have standard dislocation creep. I should probably say also in these models I present, going to show you, there's no buoyancy inside the Stokes equation. So it's purely passively driven. So given the Newtonian rheology, so there's no strain rate dependency and there's no grain size dependency in the rheology, and we assume a uniform grain size, we get a very similar picture back from what was shown at the beginning of the talk, such that this is, along the bottom we have distance from the ridge axis, we have depth, the black shows the streamlines for the mantle, the purple shows the streamlines for the melt, and the colour is log base 10 of melt fraction, so this is 10% and this is 1/10 of a percent. And what we find is a high melt fraction region at the top of our domain, which is the base of the lithosphere, and we see that streamlines of melt go up vertically and are focused towards the ridge axis. And obviously some melt doesn't get focused across. Sticking with the Newtonian rheology, but investigating the variable grain size, this is ultimately some form of test on our initial hypothesis that permeability gradients from grain size will be able to affect the melt flow and focus them. What we generally see then is that the melt continues to travel vertically under buoyancy until it reaches again the base of the lithosphere and is focused towards the ridge axis. There's focusing, the streamlines from this region are focused over towards the ridge axis sooner. They're deflected over from the buoyant direction. This will most likely be due to a different spatial distribution of the decompaction length. So it's not inherently something to do with the permeability structure in place by the grain size distribution. We then consider a non-linear rheology with a variable grain size present as well. So the permeability and the rheology are a function of space. Again, we have distance along the bottom, depth along the side. Black is streamlines for the mantle, and purple is streamlines for the fluid flow. The colour again shows you log 10 melt fraction. I guess one of the most striking things now is that we have a distribution of melt which has some form of side to it and a reduction over here. We have a collection of melt here as well. Something that should be highlighted strongly and is something that raised quite a few questions is this region encompassed by a white contour. Within this region, the melt is going downwards. It's not rising vertically upwards under buoyancy. Rather, the vertical component of melt in this region is directed in that direction. That leads to melt, which is here, being brought down on this streamline, back up and in. But it's producing this almost a melt transport barrier, in the sense that if you're melt generated here, then you can't go up above it, and if you're melt generated here, obviously you can't go down through it. So everything in this region is kind of pushed over laterally, and that's giving us this strong-sided shaped feature here. There's some melt in this example that isn't focused across, and that's pooling over here in this direction and enriching the lithosphere.
Right, how much does that depend on spreading rate?
How much does what part depend on spreading rate? That triangle doesn't, well, it seems to be present for most spreading rates. This, what I'll get onto in a bit, or hopefully convince you of, and then firm up by showing you the fields at the end, is that this is a feature that results from gradients in viscosity and melting rate, and the melting rate is more or less set, but it's the viscosity contrast that comes through that causes this feature to develop. And so with different spreading rates and different rheological choices, this low viscosity band can move around a bit, but it's ultimately going to come down the side of the strong melting region and then run off along here. But I'll show you that in a bit. So like I said, the melt velocity is downwards in that region. So constructing a simple model to try and explain where this downward melt velocity is coming from. I take the standard equations, remove the shear stresses, and make the assumption that the melt fraction is small, and arrive at these equations here. So this is your compaction pressure. This is gradients of permeability and buoyancy, and this is the separation flux, or the Darcy flux for the system. You then non-dimensionalize it, and what we find is that there's these characteristic numbers at the bottom. The characteristic numbers here. So L is a parameter I've used to non-dimensionalize the gradients. So we're interested in gradients of lambda compaction length. So if lambda equals 1, then we're talking about a situation in which the gradient is of a property is happening over a compaction length. And then we have this non-dimensional number here, which will be important, which will be the reason for the downwards melt transport, which is essentially the ratio of some form of melting rate pressure, which is melting rate times bulk viscosity over mantle density, and then it's divided by buoyancy. So when it's 1, then these two quantities are equivalent. Right, so take these equations and investigate the individual effect of gradients in permeability and gradients in melting rate. So this sort of term here and this sort of term here. The first column I show you is where we just consider no melting rate and there's a gradient in permeability. Unfortunately, my grey hasn't come out onto the projector. So there should be a grey box between here and between there, telling you that within plus minus half a compaction length, there is a change in the physical background quantity. The change in quantity there is a change in permeability. So what we have in the background is a permeability that is uniform, reduces by a factor of 2 over compaction length, or half a compaction length, and then stays uniform again. And this is the resulting separation flux, which many of you will be familiar with. So the flux remains uniform here and here because the permeability is uniform, and then there's a smooth transition from the two cases from the equations. Next part that we consider then is the gradients in what I'll call here this P gamma, which is gradients in gradients in melting rate times bulk viscosity. In this column, it's the same region of space that's been altered. But what we've got is a constant permeability and a constant background viscosity. But the melting rate has changed by a factor of 2. So in this case, the melting rate would be uniform and non-zero. It would drop to half its value and then be uniform again. What we see is here is 3 cases. So I've got 2 times gamma naught, and gamma naught over 2, which is just a parameterization where I've changed the magnitude of the melting rate. So the gradient in melting rate viscosity has produced a pressure gradient that has reduced the separation flux. In this case, it's greater than buoyancy, and we have a separation flux that goes negative, i.e. melt in this region will travel in this direction. Beneath that, we have positive separation flux, and above that, we have positive separation flux. So melt will go vertically upwards in both these. What you may then expect then is melt to collect in this region here if it were to be run forward in time. But this would be a melt transport barrier. We've reduced the magnitude of gamma, and as you see, the pressure gradient as a result is reduced, and so the separation flux remains positive through the column, as highlighting some of the effect of that parameter, but I'll get onto that one later, the non-dimensional parameter. And this one, again, we're still considering variations in melting rate pressure. But we consider the melting rate is equal to gamma naught, so it should coincide with this solid black line here. It's the same case in principle. And gamma equals 0. The gamma equals 0 is a trivial case, but it just demonstrates that we need a non-zero melting rate in order for this pressure to exist. And these curves differ slightly by about 2%. They differ by changing the viscosity instead of the melting rate. And the difference comes from the fact that the compaction length is now changing along here, and so the gradient with respect to the compaction length is a change in quantity. And then we consider both of these things changing at the same time. So again, it's a uniform permeability. Both of them change. And you can see, comparing this to the solid black line here and the solid black line there, obviously they couple to produce a stronger effect for the same size of respective field change over space. And so in this region we have again, we've achieved a downward propagating melt, and here we have upward. We then consider all 3 of these things running in parallel. So we have a reduction in permeability as we go up, a reduction in melting rate, and a reduction in viscosity. Then what we see is in this panel is a superposition, as it were, of this one and this one, which highlights the role of permeability. Permeability isn't acting as a force in this at all. It's modulating the response. And the gradients in melting rate pressure are what's generating us a pressure that's able to drive melt against the buoyancy direction. This is the parameter space. All I really want to show then is that we have this this non-dimensional number, which is just the ratio of melting rate pressure divided by buoyancy. And then we have the length scale over which these gradients happen. And in all of this black region, we've got melt that is going against the buoyancy direction. In this direction, it's all going in the buoyancy direction. And these symbols here, just to note, this case, this one, and that one. So you can see how close they are to this line, which is a scaling analysis of where the transition is. So, and that's a reduction in melting rate, an increase in melting rate. So putting all this back together, I show you the fields for the fast spreading ridge that I showed you initially, which had downwards propagating melt in this region, and a well characterized and shaped melting region distinct from that which was predicted from previous models. So what we can see is the grain size is not really changing drastically in that region. Yet we wouldn't expect it to be a big contributing factor at this stage, because I've said it's the viscosity and the melting rate. But what we do have is strong gradients in melting rate as we go vertically up. And more importantly, we also have strong gradients in the viscosity. And when these two are coupled, it's this region, therefore, that we're able to drive melt against the buoyancy direction. So I'll finish it there and just say that the permeability is modulating the melt transport, but it's not the grain size through the permeability that's able to have much influence. It's more this melting rate pressure gradients that are a function of the rheology and the melting rate, and rheology can clearly be a function of the grain size and strain rate. And what we're doing then is moving from a picture with this more complicated rheology, moving from a picture of a classic decompaction channel with melt transporting here to one where we're able to move melt towards the ridge axis, in fact get downward propagating melt, but we're getting a cleaner sided feature which would be in closer agreement with the observations than the ones we would have previously predicted. I think that's all I've got to say.
Thank you very much, Andrew. Questions? John?
Yeah, nice work, including lots of interesting microscopic physics. But as an experimentalist, I feel a little bit uneasy because, in a way, you apply, in my opinion, very poorly constrained experimental observations. For instance, grain growth. The purely my data, I don't think my data are useful because there's a huge difference between pure single phase and two phase. Huge. Yeah, some parameters are different by million times. And rheology, so-called dislocation creep, power N3, 4, diffusion creep, those are pretty well understood. But somewhere in between is extremely poorly constrained. So you got to be very careful whenever you use raw data. That's my comment. I can talk to you later.
Yeah, great, thanks.
Would there be any interesting geochemical predictions from these different bits of up and down melting? Yes. What's that? Okay, well, no. Gareth?
I was just curious about that sort of high porosity wing out there. And how does your melting rate depend on pressure? What's your productivity, DFDP? Is that constant? Or does it vary? Does the melting rate change very much as you go up the melting column?
As you go up the melting column?
Yeah.
I don't know, Rich, maybe you want to...
Picture, I think, of the melting rate.
Oh, so you're using the CATS?
I'm actually using the melting model that Toby's been working on,
Okay,
and so I guess
that's more
he can help you out tomorrow.
Yeah. Just trying to get a sense for how much melt is actually being generated on the side, and therefore how robust that.
Maybe I can quickly, sorry, Rich.
Maybe I could just quickly add that if in a picture where the melt flow pattern is relatively uniform, the melting rate would also be relatively uniform until you hit the thermodynamic barrier. However, the melting rate actually couples with the compaction rate, which couples with the rheology, which means that you wouldn't expect in that modified picture the melting rate to have the same pattern as otherwise. So all of these things are non-linearly coupled. So it would actually be interesting to maybe later look in a discussion, look at what the melting rate actually looks like for this particular run, if the data is.
Yeah, no, just some clarification. I'm still confused about the direction of things. So that's a great picture right there. So yeah, there should be a pressure due to the melting rate times the viscosity, but both of those are largest to the side, so the gradient is actually, I would think the high pressure region should be towards the axis pushing melt out, not the other way around. Large melting rate goes to lower melting rate, higher viscosity. Just if I look at the size of the direction of the pressure term, the gradient's high pressure to low pressure is that way, not that way. So I'm confused. Does that make any sense? There's a pressure due to gamma delta V, the volume change, right? So that's positive where gamma's positive. Okay. It will be convolved with the viscosity, but that's also high where gamma's large, right? So the pressure should be high there, should be pushing melt out, not pulling it in.
I mean, the delta V is zero.
Sorry?
There's delta. We use the extended Boussinesq approximation, so delta V is zero.
Well, then there's no, then I have to go back and think how gamma is coupling to the pressure, because there is a piece of the pressure that's, okay, so you're taking rid of that one.
Yeah, but it's more complicated with delta V.
Well, but then maybe you should actually, that part might not be negligible in this calculation. You've got some big numbers in there. It's worth looking at, because it'll counter that direction.
Okay, I'm not an MT person, but I think just based on my conversations with MT people, I would caution you to not overinterpret the shape of that EPR image, because the MT inversion is extremely nonlinear, and so it does depend a lot on any kind of regularization or how they do the inversion. So my suspicion would be, if they made that a relatively